This video is about surface integrals of vector fields or flux integrals. We're going to discuss orientable surfaces and oriented surfaces. We'll talk about how to find the upward unit normal and downward unit normal given z is a function of two variables, x and y. And we'll talk about how to find the unit normal vectors for parametric surfaces. Then after that, we will discuss what are called flux integrals. And flux integrals are surface integrals that allow us to calculate the volumetric flow rate if F represents the velocity field of a fluid. Now, if F has some other interpretation, the flux integral is well defined as well. But this gives us something to visualize and something to think about when we're looking at this flux integral, the surface integral of a vector field. Here's the idea. Let's say I've got some surface like this, and maybe the velocity field of the fluid is represented by all of these little red vectors. Well, if the fluid is moving through the surface this way, I might be interested in how much fluid is moving through the surface per unit time. And it turns out that I can find out how much volume is going through the surface per unit time by calculating a surface integral. I'm looking at the amount of fluid that goes through that little patch per unit time. We'll be able to find that using a surface integral. Now that's giving us volume through the surface per unit time. If we take that volume per unit time and we multiply by density, that's mass per unit volume, we're going to get a mass flow rate, the amount of mass going through the surface per unit time. And then we'll talk about how to set up the flux integral when z is a function of two variables. And we'll talk about how to set up the flux integral when the surface is defined parametrically. So let's look at this definition first. Got an orientable surface. And again, this is important because it matters which direction we decide is the positive direction. If you get a volumetric flow rate and it turns out to be negative because you were counting all the volume that was going through the surface in this direction is positive, but it actually turned out more volume was going in this direction, well, you can interpret that negative volumetric flow rate as saying that the volume is actually going in the opposite direction from the direction that you were expecting. And that's useful information. But if we don't have an oriented surface, so we don't have a distinct upside and a distinct downside to our surface, none of that really makes sense. So that's what this terminology is all about. So let's define an orientable surface. It's a surface for which the unit normal vector n hat can be defined at every non-boundary point in such a way that the normal vectors vary continuously over S. It's a surface with two distinct sides. That's really the way I think about it. This surface that I draw all the time, this cartoon of a surface, it's orientable because that's clearly the upside, it's the top, and the bottom is below it. This is also orientable. Closed surfaces are orientable. It has an outside and an inside. The surface on the outside, that's the surface that's closest to us, like that's over here. We could put a unit normal vector on that that's pointing out. We could also put the unit normal vector or orient the unit normal vectors in such a way that they were all pointing in. But it definitely has an outside and an inside with that closed surface. Now, if you're thinking to yourself, aren't all surfaces orientable? I mean, don't all surfaces have this property where the normal vectors vary continuously? Well, actually, it turns out that there are some surfaces out there that aren't orientable. Here are two examples, a Mobius strip and a Klein bottle. Now, I can make an orientable surface out of a strip of paper like this. So this is just a strip of paper. There's actually some notes that I made. If I just join those two ends, this is an orientable surface. It has a distinct side over here and then a distinct side over here. So this is orientable. Now, if I twist this, now I've got, I know it's got some hard edges, it's not supposed to. Now I've got what's called a Mobius strip. Now, if you are on this side of the surface, like let's say you're on the outside and you're sort of on the surface, eventually you get to be like on the inside. It's strange. I'm going to show you, there's some nice GIFs online of Mobius strips and Klein bottles. So here is a Klein bottle. You see how that normal vector sort of abruptly changes sides? Like if you're on the inside, eventually you end up on the outside. If you're on the outside, eventually you end up on the inside. It's a very strange. Here's a Mobius strip. See those ants? They're crawling along on the surface and then suddenly they flip. Now that might just be a consequence of the design of the GIF. But that's the idea. It's that unit normal vector abruptly changes from one side to the other side. So that is, or those are non-orientable surfaces. Now an oriented surface is an orientable surface with a chosen unit normal vector that allows us to indicate orientation. Now in this class, we tend to choose upward unit normal vectors. Now the way we do that for a surface given by z equals g of x, y is exactly the same way that we found normal vectors when we were finding tangent planes in the chapter on vector valued, or on the chapter, in the chapter on functions of several variables. We take our function, which is now represented by g instead of f because we're using f for something else. And we sort of set one side equal to 0. And the way we tend to do this so that we can get the upward unit normal vector we want is we say, let's let capital G of x, y, and z be z minus this little g of x and y. Now, if you're saying to yourself, isn't that 0? It doesn't really make sense to call that a surface. You're right, it is 0, but it does make sense to call that a surface. Let me give you a concrete example. If z is equal to x squared plus y squared, and I subtract x squared plus y squared from both sides, I get capital G of x, y, and z is z minus x squared minus y squared, and that equals 0. This equation is equivalent to that equation, but this equation is easier, or this equation is in the right form to find a normal vector to the surface. This one I can find the gradient, which tells me the direction of steepest ascent or the direction of greatest increase of z, but I'm not really interested in that. What I'm really interested in is a normal vector to the surface. I need it written in this form if I want a normal vector to the surface. So I write this function in this way. I have z minus that function of x and y, and then in order to find a normal vector, I just take the gradient of that function. Now, in terms of little g, the original function, the partial of this function with respect to x is, well, 0 minus the partial of little g with respect to x. And the partial of this function with respect to y, well, is 0 because there are no y's in that, minus the partial of little g with respect to y. And the partial of this function with respect to z is 1. Now that is a normal vector. If I want it to be 1 unit long, I need to divide by the magnitude. And notice that when we take the magnitude of this, we get 1 plus the partial of g with respect to x squared plus the partial of g with respect to y squared. If that reminds you of surface area, that's a very good thing, because that is that extra factor that we see whenever we calculate ds. So that's going to be very nice. It's going to come in handy later, and it's going to cancel. So it's going to be very, very nice. But that gives us the upward unit normal. And if you're saying, how do you know that that's upward? It's because this z component is positive. So that means it's an upward unit normal. Now if I take that and I multiply by -1, that gives me another normal vector. It's just the downward unit normal. If I multiply each of the components by -1, I get this. And then the z component is negative, so the vector is pointing down. Just briefly, let's look at finding the upward and downward unit normals for a particular surface. So first we take this z as a function of two variables, x and y, and we rewrite it this way. We say capital G of x, y, and z is this. After you've computed g, then you take its gradient, and you could use that formula on the other page. I just look at the formula here and take the partial with respect to x, with respect to y, and with respect to z. So I get -2x, -2y, and 1. And I know it's an upward unit normal because that's a +1, and I want an upward unit normal generally. In order to find n hat, that is the upward unit normal. This is a normal vector, but I want the unit normal. I take that and I divide by its magnitude. If I want the one that goes downward, I just take this vector and I multiply it by -1. It doesn't change the magnitude, so that number in the denominator is the same. Now, if I evaluate this at a particular point on the surface, say x equals 1, y equals 1, z equals 2, then I find out that my upward unit normal looks like this. So we're at 1, 1, 2. We go back 2/3 of a unit in the x direction, 2/3 of a unit in the y direction, and our z value goes up by 1/3. So it sort of points in, it points toward the z-axis in our elliptic paraboloid. And this downward unit normal is exactly like that, but it's going to be +2/3, +2/3, -1/3. It's pointing the other way. And it's pointing sort of outside of our elliptic paraboloid and pointing down, which I think makes sense. If we actually had one of those in front of us, I think we could see that the normal would be pointing down a little bit if we created it on the outside. Now, if we have a parametric surface given by r of u and v, remember what we talked about before. We said the unit normal vector n can be found by taking this, or the normal vector n can be found by taking this cross product. Well, if I want it to be a unit normal, I just divide by the magnitude. Now, this is going to point in one direction. If I change the order of this cross product, I get the other one. That points in the opposite direction. One of the downsides of using the parametric surface is that it's not obvious from looking at either one of these formulas which one is the upward unit normal. One of them points up, the other one points down, and we can't really tell which one is which. Now, in practice, for a particular parametric surface, you can calculate this vector and then look at the z component and then look at the bounds, because this is usually our surface for all uv in some region D, and D is given to us. D is specified. So you can look at the requirements for U and V while you're in D and see what happens to the Z value. You want to choose the one that will make the Z values positive if you are looking for an upward unit normal. But that's a downside. I prefer to do this because then I know that this is the upward unit normal. Over here, it's less obvious, but it can be done if we have U and V and D. Okay, let's do some examples. Oh, actually, we have to talk about the flux integral now. Now we have everything that we need to orient a surface. We can define a normal vector for an orientable surface. We can call it the upward unit normal, we can call it the downward unit normal, but we can choose whichever one we want. If it's a parametric surface, we can choose one of these and we can decide whether it's upward or downward using D. And then we can use that chosen orientation to define a flux integral. So let's say we've got the F here, and F represents the velocity of some fluid. Well, if I want to know the amount of fluid going through the surface per unit time, What I do is I take my surface and I break it up into a bunch of little patches like this. And if I focus on that one patch, it turns out that that volume of fluid moving through the surface per unit time is equal to this. So let's say while you're on this patch, which is relatively small, this is the velocity vector, F for the fluid. And while you're on this patch, our unit normal vector is pointing up like this. Well, if I make a little, it looks like a parallelepiped. It's hard to draw. Yeah, it's really hard to draw. Going over that patch. The volume of that parallelepiped is going to be the volume of the fluid going through the surface. I know that seems very odd, but it is, and I'll show you at least, I'll show you some justification for that using the dimensions of everything in just a moment. So I look at the volume of this little box or the parallelepiped there. It's going to be the area of the base, which is delta S sub I. It's the area of that little surface patch, times this height. Well, that height is just the projection of that velocity of the fluid onto n hat. And the projection of F onto n hat is given by the dot product of F with n hat, and then we divide by the magnitude of n hat, but n hat is 1 unit long. So that is the amount of volume going through that surface, that little patch, per unit time. Now I know it does not look, it's not at all obvious that that's volume, volume of fluid going through the surface per unit time, but we'll show that on the next page. Well, we add all of that up for all of the little patches here, and that's giving us this flux integral. Or we could say the surface integral of a vector field F. So I have the double integral over S of F dot N times ds. And if F represents the velocity of some fluid, this double integral of F dot N ds is the flux of, it's like fluid through the surface, or we should say the volumetric flow rate. It's the volume of fluid moving through the surface per unit time. Now, I've talked to a lot of students about this, and they always say, like, how do you know? And why on earth would the volume of that little parallelepiped right there, why should that have anything to do with the volume of fluid going through the surface? Well, it's a fair question. It's a very fair question. I'm not sure that I'm going to do a very good job arguing for it, but I think if you just look at the dimensions, it actually makes a lot of sense. I accidentally grabbed a green marker. I don't want to use green. Excuse me. This is a dot product with a unit vector of the velocity of some fluid. So let's say that velocity is measured in, let's say, meters per second, just for example. Well, then this area, if F is measured in meters per second, hopefully our surface patches, S, are also measured in meters, but they're meters by meters because it's a surface area, so it's meters squared. Just by multiplying those dimensions, you see you have meters per second times meters squared. Well, what do you get from that? That's meters cubed per second. So it makes perfect sense that that would be volume going through the surface, because I've got velocity times area, which seems strange. But if you just look at the units, meters per second times meters squared, that's meters cubed per second. So that's giving me volume through the surface per unit time. So that is sometimes called the flux integral. But again, it's giving you volumetric flow rate, volume through the surface per unit time. And if you want the mass flow rate, and you happen to know density, well, you just take your density, which is mass per unit volume, and you multiply by volume per unit time, and then you get mass per unit time. So this is the density of the fluid. And when I say mass flow rate, what I mean is the mass of the fluid moving through the surface per unit time. Okay, so those are the definitions. Here's my surface integral of a vector field. Here's what it means when we have the velocity field of fluid. Here is my mass flow rate integral. Okay, now these are not useful. Just like before, I've got way too many variables. I want to do a double integral over this surface, but I've got F, that field, it varies for every x, y, z. You have the normal vector that varies while you're on the surface. And then we're integrating over all of these little surface patches, and we prefer not to be integrating over surface patches. So what we do is kind of what we did before when we were talking about surface integrals of scalar functions. We'll look at the projection of our surface onto the xy plane. Oops, it's g of xy. And rather than evaluating a double integral over S, we can evaluate a double integral over R. I've had too much coffee. It's making all these little errors and I'm making them fast. Sorry, guys. Okay, so I'll take my surface, I'll look at the projection onto the xy plane, and then I can write everything here in terms of x and y. And that's if z is given by a function of x and y. If our surface is given parametrically, we'll handle this differently. But let's look at the first case, where z is a function of two variables, x and y. Well, in that case, the surface integral over S can be written this way. Now I'm going to go through a couple of steps in the derivation, and then I'll put a box around the answer that we actually use. Rather than looking at the integral over the surface, we'll look at the projection onto the xy plane. Now, our field needs to be written in terms of x and y only. So we've got f of x, y, and everywhere you see a z, z needs to be replaced by z of xy or little g of xy. Either one is fine. They mean the same thing. Now, if we are dotting that with the unit normal, remember how we calculated the unit normal. The unit normal was given by the gradient of capital G divided by the magnitude of the gradient of capital G. And then ds was equal to this. We took the partials of z with respect to x and y on our surface and we put them there. And z is given by little g of xy now, so we're going to write it that way. So this is ds. But remember what that magnitude is. If capital G is z minus little g of x and y, then the gradient of capital G is this. And when I compute the magnitude of that, I'm going to write it in a slightly different order. And a negative squared is the same as the same thing, but positive squared. I get that. So I have that magnitude right there and right there. So it's going to cancel. It's going to cancel every time. I'm not, yeah, so I've got that. And then this is divided by, well, exactly the same thing. And check it out, they cancel. And so what do we get? What's the version that we actually use? We don't use that version. This is it. You take the double integral over R of your field, evaluated in terms of x and y. And then you multiply by the gradient of capital G. That's it. It's actually super simple. And this is where we're treating that upward direction. We're using the upward unit normal here. So if fluid is going from the bottom of the surface to the top of the surface, if the fluid is flowing through in that direction, we're counting it as positive. So this is our flux integral, and this is how we evaluate it. Okay, now let's look at the other flux integral. We'll use this in just a moment. Well, it's exactly the same flux integral, but let's look at our alternate representation of the surface. If R is given by, or if the surface is given by R of u and v, and R has components x of u and v, y of u and v, and z of u and v, for uv in some region in the xy plane, or no, in the uv plane, excuse me, d, well, rather than evaluating the double integral over the surface, you will evaluate a double integral over this region D. So the goal is to just reduce the number of variables. We'd like to take this double integral that involves lots of different variables and write everything in terms of u and v. So we will. Easy enough. I need my field in terms of u and v. Well, initially your field's in terms of x, y, and z. So you just replace your x with x of u and v. You replace your y with y of u and v, and you replace the z with z of u and v, and then you dot it with the normal vector for this parametrically defined surface. Now remember what we calculated as the normal vector earlier. That was the partial of r with respect to u crossed with the partial of r with respect to v. Don't take the magnitude. We want the vector itself. You're going to compute a dot product. Actually, that's not the unit normal. So that's a normal vector. And then we divide by its magnitude. That's n hat. Now ds, it's kind of like what happens over here. ds, that's the surface area of that little surface patch. Well, that was that area of the parallelogram with these two partial derivatives as adjacent sides. So the area of that parallelogram was the magnitude of that cross product as well. Took that area and we multiplied by du dv. And so those guys reduce. So in practice, rather than evaluating this, if you've got a parametrically defined surface, you write your field in terms of u and v. You compute this cross product. You take a dot product and you evaluate the resulting double integral over d. So these are flux integrals. Flux is what we're trying to find. More specifically, that's volumetric flow rate, volume going through the surface per unit time. Question is, how do we find it? We evaluate that this way if z is a function of two variables, x and y. We evaluate this way if our surface is defined parametrically by r of u and v, where u and v are points in the region D. Okay, so let's use those formulas now. I like this stuff. I actually had a student last semester who was like, this is not that impressive. Like, really? Like, less than 2 years ago, the most advanced thing we could do was find out the distance to cross the lawn on campus or something like that with the Pythagorean theorem. You know, we didn't, in your pre-calculus class, there wasn't a lot you could do with that math. I mean, we said, oh, look at this application. Are you ever really going to use the Pythagorean theorem to figure out the distance to cross the lawn on campus? Probably not. But are you ever going to be interested in a volumetric flow rate? Do you want to know how much volume is moving through a surface per unit time? Heck yeah, if you're an engineer, you are. Like, this math is allowing us to do things that we could never do before, not with pre-calculus. And even single variable calculus was somewhat limited, but with multivariable calculus, with our knowledge of vector fields and surfaces and curves, and substitution, because that's all this is. It's just a lot of substitution. We're able to calculate things that we could never calculate before, which I think is really cool. All right, let me get off my soapbox now. Is that soapbox? Maybe using the wrong term. Okay, let's say you've got, this is your field. So f of x, y, and z is x times I hat plus y times j hat minus 2z times k hat. And we want the first octant portion of this surface, where s is given by x squared plus y squared plus z squared equals 36. We want to find a volumetric flow rate. So we want to find the volume of fluid moving through the surface per unit time provided that F is the velocity of that fluid. Okay, so they tell me that they're looking for volumetric flow rate, so I know immediately that this is what I want. And I know since Z, well, actually I've got Z defined this way. So that's going to be a little different. I need to get F in terms of X, Y, and Z this way. I need to get the gradient of capital G over here. All right, so this is going to be a little different because Z isn't already by itself. That's okay. But what we're going to do is we're going to look at our surface S. We're going to take the projection of S onto the XY plane. Then we're going to write F in terms of X, Y, and whatever Z is in terms of X and Y. Actually, we can see what that is already. I'll just write Z of X and Y for right now. And we'll dot that with the gradient of capital G and multiply by dx dy or dy dx. Okay, so I guess the first thing we need to do is we need to sketch our surface so that we can find the projection onto the XY plane. We want the first octant portion of this. Now notice we've got X, Y, and Z all squared. There's nothing in the denominator. I'm not subtracting anything from X, Y, or Z. And the right-hand side is 36. That's a sphere of radius 6 centered at the origin. Now we actually don't get the whole sphere, we just want the first octant portion of it. .36, not 6. Okay. And the region R is that part of, or that projection of that part of the sphere onto the XY plane. Since we're in the first octant, looks like this. That's probably best described in polar coordinates. R goes from 0 to 6. Theta is an angle that sweeps. It starts over here at 0 and it goes to pi over 2. Okay. Now again, I generally don't recommend that you try to go straight to polar coordinates. I recommend that you go from your surface S to your integral in terms of X and Y. And then maybe after you find this integrand, then if you see that polar coordinates make the most sense because this region R is part of a circle, then I would switch everything to polar coordinates. But we always want to start this way. So first we graph the surface. I'm going to sketch the projection onto the XY plane. All right, and now what do we need? We need our field in terms of X and Y and Z. In order to get that, I need to find Z as a function of X and Y. So I will solve the equation for the surface. So they solve the equation of the surface for Z. I have Z equals the square root of 36 minus X squared minus Y squared. Ooh, that's looking really nice for polar coordinates, isn't it? And then we want to write our field in terms of X, Y, and Z. Or excuse me, X and Y only. So our field was originally X times I hat plus Y times J hat minus 2 times Z. want to replace your z with whatever it is in terms of x and y on your surface. And it just so happens to be the positive square root of 36 minus x squared minus y squared. Okay. Now I just need the gradient of capital G. So I need to find capital G and then compute its gradient. So you just take this equation and you subtract that square root from both sides. And then we want the gradient of that. Okay, now for the partials with respect to x and y, we'll have to use the chain rule because we've got an inside function. The derivative of z with respect to x is 0. And we'll have the derivative of this negative function to the 1/2. That's negative 1/2 times my function to the 1/2 minus 1, that's negative 1/2. Times the derivative of the inside by the chain rule. With respect to x, treating y as a constant. And we're going to get pretty much the same thing with respect to y, just the derivative of the inside with respect to y is negative 2y instead of negative 2x. Put your inside function back in. And the derivative of this with respect to z is 1. That's an upward pointing normal because that z component is positive 1. The 2's reduce, the 1/2, the negative 1/2 and the negative 2. And what we get for g is x over this square root. And then we have y over this square root. And z equals 1. Okay. Still, I'm not really excited about that, but that's all right. So we've got the gradient of capital G now. I need to take the dot product of that and then consider integrating over R. So we found G, we find the gradient of capital G. And now we want the dot product. So that was x, y, and negative 2 times z, which is given by this, dotted with that vector right there. Oops, that should be under a radical. So I'll have x squared over this. Oops, we're taking a dot product, so we multiply and add. Multiply y times that y is going to give me a y squared in the numerator. And add, multiply, and add. Now right away I notice I've got 2 of the same denominator here, so I can add the numerators. Now over here, want to write that as itself over 1, we can multiply the numerator and denominator by that root to get a common denominator. Let's see what happens. Got x squared plus y squared minus 2 times that quantity. Square root times itself is just that expression under the square root. Okay, and distribute the negative 2. X squared plus y squared minus 72 plus 2x squared plus 2y squared. Man. A lot of algebra. And we got 3x squared and 3y squared now, minus 72. I guess we could factor out a 3 from everything up there. I'm not sure that that would help us though. All right, so that is my integrand, the double integral over s of f dot n ds is equal to the double integral over r of this function. Now our region R looks like this. R goes from 0 to 6, and theta goes from 0 to pi over 2. That worries me, because when R equals 6, we're dividing by 0. It's a bit of a problem. Okay, so let's write everything in terms of polar coordinates. So theta goes from 0 to pi over 2, R goes from 0 to 6. We've got 3 times x squared plus y squared can be replaced with an r squared. And then down here we've got 36 minus r squared. And that dA can be written as r dr d theta. I think that works, but it doesn't work out very nicely, does it? It's a bit of a problem. We're dividing by 0 here. Maybe there was a different way I should have written that unit normal vector in that case. But it's an improper integral. I think we can evaluate it as an improper integral and get a finite limit for the flux through the surface. Now, I'm just not sure that I want to, though. I mean, it's not too bad. It's just not great. Notice that none of this inside depends on theta. All of this is constant with respect to theta. So we could just evaluate the integral from 0 to pi over 2 of 1 with respect to theta. That's going to give us theta evaluated from 0 to pi over 2, or just pi over 2. We take that and we'll multiply by this over here, which is an improper integral. So I had to take the limit as r approaches 6. That's going to be from the left of this guy. And maybe we should take out the 3 as well. There we go. All right, I wrote r approaches 6. Let's do b. Let's let b approach 6. So we have the integral from 0 to b of r squared minus 24 times r over the square root of 36 minus r squared dr. And we can use integration by parts. I'll let that be u. I'll let this all be dv. oops. When you anti-differentiate this using a u substitution, you're going to have u raised to the positive 1/2 times 2. That's going to be the antiderivative of that. But the derivative of the inside was negative 2r, and there's only an r. So we should also have a negative 1/2 outside. So let's check. If I take the derivative of that, do I get that? Yeah, I do. So I'll have 1/2, negative 1/2, 36 minus r squared to the negative 1/2 times a negative 2r. Yep. Okay. We're using integration by parts. We do this times this minus that times that. And we're multiplying that result by this 3 pi over 2 over here. So we've got uv minus the integral of v du. So we're subtracting a negative, that's going to be adding. We're evaluating all of this from 0 to b and taking the limit as b approaches 6 from the left. Oops, there's a dr missing. Okay, so that's a negative integral of u to the 1/2. So we'll have u to the 3/2. And we'll divide by the 3/2, which is multiplying by 2/3. Evaluate all of that from 0 to b. Now I'm doing a lot of u subs in my head here. You don't have to do that. If you want, you can stop and do the u sub. When I evaluate this at r equals b, I get this value. When we evaluate this at r equals 0, we're subtracting. This will be subtracting 24 times the square root of 36. So 24 times 6. And then we're subtracting a negative, so that's adding 2/3 of 36 to the 3/2. So that's 6 times the square root of 6. Okay. And as b approaches 6 from the left, this is going to approach 0, this is approaching 0, and we just get that number there. And so we get whatever that is. What is that, 120? And then another 24, 144. And, oh wait, that's multiplication, not addition, sorry. That is the flux through the surface. Man, okay. I think for the next one, we're just going to set it up. We're not going to evaluate it because it just takes too long. But here's the idea with the surface integral. You've got to sketch this surface S, look at the projection R into the XY plane, find your field in terms of X and Y, find your normal vector in terms of X and Y. It doesn't have to be a unit normal. You just find the normal because the magnitudes cancel out from the ds. and then you multiply by dx dy or dy dx. So we got to right here, and we said, that looks like a good candidate for polar coordinates, and we did this, and then we evaluated this using some old methods from Calculus 2, like integration by parts. Okay, so now we're going to do this for a surface integral, or not a surface integral, for a parametrically defined surface. So let's say our field is given by z times I hat plus x times j hat plus y times k hat. And we've got a parametrically defined surface, r of u and v, which is given by u plus v squared times I hat, and u minus v times j hat, and u squared times k hat, where u ranges from 0 to 2, and v ranges from -1 to 1. Now this is not one that I'm familiar with. When I look at those formulas, it's not clear what the surface looks like, but it looks fine to me. Looks like we should be able to calculate everything that we need to find flux. Okay, so we want the flux through the surface integral. And so we want our field entirely in terms of u and v. So the field F needs to be written in terms of u and v. And then this normal vector, the unit normal, is this divided by its magnitude, but the magnitude from this denominator cancels with the magnitude of that vector for the surface area piece, and we just end up with a du dv over here. So we just need the field in terms of u and v. So we replace x with x of u and v. We replace y with y of u and v, and z with z of u and v, where x is the x component of our parametric surface, y is the y component, and z is the z component. You substitute those in over here, and then you compute those two partials, you take a cross product, you take a dot product, and then you're going to integrate over that region, which is just constant to constant, very simple integration. Okay, so let's find the field in terms of u and v first. So it's z times I hat plus x times j hat plus y times k hat. Z is u squared, and x is u plus v squared, and y is u minus v. Okay, so that was easy enough. Okay, now we need to find those two partials. So the partial of r with respect to u is easy to find. We just take the partial with respect to u of each of those three components separately. Oops, not plus. So you get a 1 and a 1 and a 2u. Not bad. That's going to be super easy to take the cross product with. And then we look at the partials of each of the components with respect to v. So there's no v here, so that's 0. The derivative of v squared is 2v. We get a -1 there, and there are no v's there, so we get a 0. So we found those two. We need the cross product now. Okay, so I've got 1, 1, and 2u. And v, -1 and 0. Cross out the row and column containing I hat. So of 0 minus a negative is plus 2u. You always get a negative for that y component. Cross out the row and column containing j hat. 0 minus 2v times 2u is 4uv. Then we cross out the row and column containing k hat. We have -1 minus 2v. Okay, so we've got 2u, 4uv, and -1 minus 2v. Now, if I'm concerned about having an upward unit normal, so I want to choose my normal vector to go through the surface, I need this z component of my normal vector to be positive. But looking at this, it looks kind of negative, doesn't it? Because it just really depends on the value of v here. Let's figure out what happens to that z component. If v is between -1 and 1, if I multiply this by -2, I get 2 is less or is greater than or equal to -2v is greater than or equal to -2. And then if I subtract 1 from all three parts, I get a 1 minus, or -1 minus 2v, -3. It looks like that z component is sometimes positive and sometimes negative. Looks like it flips sides. Guess that's okay as long as it does so in a continuous way. I'm not 100% sure about that, to be honest with you. Like, well, we can still do our calculation. Just not really sure what to make of that. So I'm not really sure which side we're counting as the positive direction when we do this dot product. Okay, so now we're going to take our field, we're going to dot it with the normal vector. And then we will integrate over this little region there. So we've got our field here, and we've got our normal. Of course, the calculations are not too difficult. I'm just a little bit unsure about that z component. And it's possible that my understanding of orientable surfaces is not quite right either. Let's see. Need to do more research. F has components u squared and u plus v squared and u minus v. And the normal vector has these components, 2u, 4uv, and -1 minus 2v. And I didn't see what was that x component. It's 2u. Okay, this is our integrand. And we're just computing that. That's our next step. We're taking a dot product. So you multiply and add this times this, and add this times this. 4uv times that. We'll distribute. And then we've got that times that. All right. And then we'll just do a little bit of foiling. First times first, outer times outer, inner times inner, and last times last. Do we have any like terms anywhere? It doesn't look like it, unfortunately. Just a big old integrand. That's okay. So the double integral over S of this, which represents flux, is the double integral over this region. U goes from 0 to 2. V goes from -1 to 1. And this is our integrand. It's that field in terms of U and V dotted with the normal vector. And we integrate with respect to V first, because those are my bounds for V, and then we've got our bounds for U. Just a bunch of power rules. I'm not going to do it, but I hope you get the idea. Okay, so let's talk about flux integral, surface integral. The flux through the surface, which represents the volumetric flow rate in the direction of n hat, that choice of n hat that we chose, is given by this. So if you want to evaluate this, and z is given as a function of two variables, x and y, you find your field in terms of x and y by replacing z with g of x, y. You compute capital G, which is z minus little g of x, y, compute its gradient. That goes right here. And then the magnitude of the gradient in the denominator and that magnitude of the gradient that showed up in our surface area formula, those reduce, and you just end up with the field dotted with the gradient of G. Multiply those two together and evaluate the double integral over R. That's just a dot product. Now this guy down here, it's actually pretty simple. If you have a parametrically defined surface, you need everything in terms of your two parameters, U and V. So instead of evaluating this double integral, you evaluate the double integral over D, where D is that region in the UV plane. You write your field in terms of U and V by replacing x with x of U and V, y with y of U and V, and z with z of U and V. You compute this cross product. You compute the two partials, you take the cross product, that's the normal vector. Now it may not necessarily be the upward unit normal, you should check. I checked and it was a little weird. It changed signs, that z component changed signs on the interval. So like sometimes it's positive and sometimes it's negative, and that worries me. So my result on that last one is questionable. But as far as the algebra is concerned, the algebra was right. I get my field in terms of U and V. I compute the two partials. I take a cross product, and that's my normal. Then I take a dot product. That's my integrand. And then I evaluate the double integral over D, and that's giving me flux through this surface that's defined by this parametric representation R of U and V.